Thanks a lot. So before I start, I'd like to thank many people, too many people, in fact. So I picked three of them. So we'll thank the other one at the end of my talk. So the first one is obviously Carl. So Carl invited me 10 years ago to work with him in the US at the Berkeley lab. So it has been since very fruitful collaboration, and also a great friendship. So I thank you. Yes, I thank him for that. The second one is Laurent Charlet. So Laurent Charlet is my PhD advisor. So Laurent was the first one who introduced me to the magic of clay surface reactivity during the courses in master, and he has always been a model for creativity for me, and also for trying to explore, I would say, many directions at once. So yes, I thank him for that. The last one I would acknowledge is Faiza Bergaya. So Faiza is a really true, I would say, clay lover. She's passionate about clay and about the clay science community. And that's something she was always eager to communicate to me. And so I really also value a friendship during all of these years. So they have very different personalities, there's two persons, but they have only, they have not only one common trait, but I would say the most important for me is their generosity. And so I'm very happy to have been mentored by these three people all over these years. So now, okay, I will enter the subject of my talk. So the subject of my talk is about electrostatics and properties of clay minerals, and how this electrostatics can help us to make a link between mineralogical properties, geochemical properties, and also geophysics. So for most of people who are interested in clay with regards to some engineering application, there are 3 or 4, in fact, properties that are really very important. That's the low permeability, the low diffusivity, and the adsorption properties of clay. Just forgot to put swelling on it with regard to this application. And so these very properties of clay minerals and clay media are very important in the framework of waste repository or isolation studies. CO2 sequestration, because you always have these cap rock properties that you must take into account with regards to gas leakage, gas storage, same kind of story that for CO2 sequestration, but also resource extraction, like in shales. And you have also other type of problems that's not this is solution, this is a problem that is related to clay. That's about, for example, the land use with this kind of shrink swell problems that can destroy the buildings. So for this kind of engineering application, then we need to understand the Clayey system, and we need to do some predictive approaches to estimate the transport and the reactivity of water, gas, and solutes in the clay materials of interest. And one of the difficulties to do that is that there is many coupled processes that link the thermic, hydraulic, mechanical, and chemical properties of this clay media. So these properties are not the only one about clay. Clay materials are very anomalous properties. So I take an example here. That's a very specific example. That's about diffusion. And that's an experiment that has been published by colleagues in Switzerland. That's that's very clever experiments. I really like this one. I think I show it at every talk I've made since perhaps 5 years. So what they did is that this is a clay sample. This is a kind of diffusion experiment in which they were looking at the diffusion of a sodium tracer, a radioactive sodium tracer. But instead of having the two reservoirs on the two sides, having the same background sodium chloride concentration, what they did is that they put some high sodium chloride concentration in this reservoir and some low sodium concentration in that reservoir. And at time 0, instead of having one reservoir spiked with the tracer, they spike the 2 reservoirs with exactly the same concentration of tracer. So what do you expect in that kind of experiment? You look at this concentration as a function of time in the 2 reservoirs. In a normal situation, you expect to have a flat profile of concentration because there is no gradient. Since there is no gradient, there should be no diffusion. Okay, that's what's observed. They observed an increase of the concentration of the tracer in that reservoir, and they observe a decrease of the tracer in that reservoir. So meaning that that's kind of seemingly uphill diffusion in the system. So that's very interesting coupled process that is happening here. So, and really need to understand this kind of process and to be able to predict them. So one second type of anomalous properties is if you have a core sample and you fracture it, then you let some water flowing in it, and at some point you will heal or seal the system. Here you can see a fracture that is measured by X-ray CT by a team at SCKC, and after some time, then you can see the fractures has been healed. So it's very important properties, mechanical properties that can be useful for example, self-sealing of materials in radioactive waste storage or CO2 sequestration problematics. At larger scale, at the basin scale, so the Clayey media, they also have very specificity, and the specificity, in fact, are not the same as a function of the site you observe. And one of the specificities is the fact that the water that is inside of the clay formation has sometimes pressure anomalies, meaning that the pressure that is in the pressure of the fluid that is inside of the clay formation is not what it should be according to the loading of the sediments and also the depth that you have at the location. And so you have sites here in orange that have pressure anomalies, and other sites that do not have this kind of pressure anomalies. And the understanding of this is still debated in the literature, and it's important if we want to do some long-term prediction. So long-term prediction, I would say that's the extreme case is for radioactive waste storage. So we need to do this kind of prediction at the scale of the geological formation, and it's depending on the concept. But for example, for European concept, we need to do this prediction for million years. So we have access to this kind of information at the centimeter scale or core scale. So, and with experiments that last from days to months. So one of the challenge to go from here to here and to be able to do good prediction, yes, to link these two. So there's kind of a paradox here because we cannot explore gigantic size of system, and we cannot study. We cannot do experiments for a period of more than a few years. So there's a big jump to do. So the paradox is when we want to do this big jump, in fact, we are downsizing our system. So we are looking at molecular scale. We are looking at very tiny time step between two processes. So the reason why we are doing this in this kind of upscaling strategy is that we think that if we understand truly the nature of the interactions we have at this scale, then if we understand that, then we can make predictions that are physically based with at the least possible empirical parameters, and then we can gain confidence in what we do here in the performance assessment calculation, for example. So it's difficult to be an expert in all of these fields. I'm not. To be honest, I would say that I've expertise that on clay media as a whole, but I have focused my expertise a lot on spectral properties. And with regards to this kind of approach, so I would say that at this scale, I'm more concerned and informed citizen. At this scale, that's really my core part of my research. I'm a developer. Here as more a user, and here I'm a trustful collaborator. So if you have questions then after the talk that concern this part, so perhaps I would have to redirect you to some of my colleagues, some are present here. So so for example, Andre, on this list of authors, so I'm very glad to work with Professor Xianyun Liu at Nanjing University, who is really good at doing this FPMD, so DFT calculation and so on. At BRGM in Orléans, so I work a lot with Sylvain Grandjean, who is really an expert on all of this diffractometric and spectrometric techniques to characterize the samples properly. So I will start my to show you how we can do this upscaling strategies with the example of adsorption. So adsorption as a macroscopic process is very simple. You take a solution with some contaminant, you mix it with some solid, and then you record what's the equilibrium concentration at the end of the experiment. And so the equilibrium concentration, it's almost always less than the initial concentration, and then you can relate what is on the solid to the diminution, so the decrease of the concentration in solution with this kind of equation. Here you can find the RD, the distribution coefficient, or KD, it's the same, that is expressed as a function of these parameters. Okay, so depending on the type of contaminant you are looking at or type of chemical species you are looking at, then you can draw this kind of graph, for example, as a function of pH. And you can see that for calcium, for example, you don't have much change as a function of pH, but you have much change as a function of ionic strength. If you look at cations like lead, for example, or metallic cations, then it's a different story. You have also this difference as a function of ionic strength, but you have also a difference as a function of pH. And this difference and this change of adsorption as a function of pH will be also dependent greatly on the lead concentration that you put in the system. So this kind of behavior has been studied for many decades now, and it's now clear that we have different type of processes going on in the system. So one of the processes is cation change. So cation change takes place in the interlayer space between clay layers, and you have also this kind of reaction that occurs on the external surfaces, basal surfaces of the clay minerals. And for the pH dependence, it's now clear that we have this ionosphere complex at edge surfaces, which can take different form. And in fact, the edge surfaces are they have acid-base properties, and then they can react as a ligand for this species in solution. Okay, so I will focus the next slide on this kind of processes. So if we want to predict this, so these curves, the classic way that has been developed now many years ago is a surface complexation modeling. In this surface complexation modeling, it's a kind of thermodynamic type modeling in which, in fact, you try to get information about the protonation, deprotonation reactions that you have at the edges. So you lose or you gain protons. And you combine that with adsorption reactions, which has, in fact, complexation, surface complexation reaction, in which for example, your metal of interest is interacting with surface to sorbed on the surface and to release some protons in solution. Okay, so the thermodynamic writing of this is here. So the key is to get this constant, adsorption constant. And so when you do measurement, so in an experiment, you have two terms here that appears. So the first one is experimental quantification. So you can quantify what's the number of sites that is linked to lead, for example, here, or you can measure also the activity of protons, that's pH, related to pH. But there's also one term that is not possible to obtain experimentally, that's the electrostatic terms. Because the surface is charged, then the electrostatic potential that is created at the surface. And because of this electrostatic potential, you have additional energetic term into this reaction, and this is taken into account in this term. So because this is model dependent, then your constant, thermodynamic constant, can only be model dependent too. There's a new way now, because there's much progress in the development of molecular modeling. So this is still model dependent, but now we can try to get some prediction from first principle molecular dynamics, for example, of this kind of parameters. And so the idea then is, okay, so if we can have some prediction for this, we can also measure this. And so we combine that, and then now we can have a comparison to check the agreement with the experiment data, and then we can perhaps also have some kind of confirmation that our model that we use for this term is not too bad. So FPMD, I'm not an expert in that. I'm lucky I work with experts in that. So it's a combination of DFT calculation and molecular dynamics. And so you can get some energetics properties in your in your system. So that's typically a sketch of the box of atoms in which the size of the box that you can model with kind of techniques. And here you can see that we need to have a clear idea about what's the structure of the clay edge to do this kind of calculation. So one hypothesis is that, okay, the structure of the clay edge is the same as the structure of the bulk layer. But is it true? So it has been an assumption for years, but perhaps we should check on that. So this is an AFM, so atomic force microscopy image. So made that 20 years ago. So the images are quite blurry. Now you can do far better with new apparatus and also new preparation procedures. But you can see that that's an MX80 smectite. So it's a single layer. Each time we look at the shape here, it's a single layer that is on the top of the sample order. And you also, okay, so do not look at the errors. That's not part of the talk today. But you can see that it's kind of a flaky shape, and the direction are not well available from that. And so one of the questions when you look at that is, okay, we do not have the atomic resolution about the clay structure with this kind of image, but we can always ask the question, okay, so on the border, is it really pristine structure or lit layer that you can find, for example, for feldspar? So recently, so thanks to former postdoc of mine, Esra Rokoglu, now at BRGM, and Sylvain Grandjean, and with the help of Alexander Glotter from Paris. So we did some imaging using high resolution scanning transmission electronic microscopy, sorry. And we're looking at single particles that were on suborder, so a single layer particle. Here this is single layer. You can see here that if we do this transect, we have a single layer, and then on the top of that another one, on the top of that another one, and then again, so we have lot that one. So it means that this is just 1 nanometer thick. And so Alexander Glotter, he did a profile looking at the electronic density along this profile. And this is what is observed. So here we are in the carbon coating that is just next to the sample, next to the particle. And here, that's the age. And the age, you can see here the periodicity, and the periodicity doesn't change with the position as a function of the distance. So meaning that the periodicity is, in fact, in good agreement with the fact that here at the very edge of the layer, we have the same kind of structure that we got inside of the bulk of the layer. So that's one hypothesis that we can, in fact, use to do the calculation. So this was done a posteriori, but still it's important to have that kind of confirmation. Okay, so we can obtain that. So in fact, we are very fortunate. So it was 8 years ago, a group, so in Nanjing University, led by Professor Xianling Liu. So they did a tremendous job on getting all of the PK value for all of the sites that you can find on the clay edges, on monolite clay edges. So what we did is we combined this PK value, and we combined that with a model for the electrostatic properties. So there's something very specific to clay layers, especially smectite, that you have here the basal surfaces, and the basal surfaces, there's isomorphic substitution, so you have a charge, so you have electrostatic potential here that is constant as a function of pH. But you have also edge surfaces, and these edge surfaces, they have acid-base properties. The charge can change as a function of pH, and so the potential is not the same, the two surfaces. And you have kind of a phenomena that is what we call a spillover effect. That means that the basal surface is interacting with the edge surfaces with regards to the potential. And then this cannot be calculated with, I would say, a classical model for surface complexation modeling. So again, we were very fortunate because some years before, in the group of Gary Esposito, they did many analyses of, okay, so a method to estimate this term, that's a two-dimensional Poisson-Boltzmann equation, and they end up, so it was the work of Ian, by the way, with a very practical equation that relate the edge surface potential as a function of the edge surface charge, and also as a function of ionic strength. So you can see here the curve, so that are obtained with this kind of model. So if you compare that with classical oxide models like DLM model or CCM model, you can see, so one of the peculiarities is that here the curve does not intersect the zero x and y coordinate. That's because in fact your basal surface that is negatively charged, so with a negative potential, is giving you your edge surface a negative potential even if the edge charge is zero. So that's very peculiar for Clayey. So if we combine all of this, and we can predict the surface charge as a function of pH and also the potential for different surfaces, and that's the curve we obtain. And so we combine that to compare with monomer titration data, meaning the acid-base properties you can get from the lab experiment. And we've got a pretty good match. So we're very happy with that. And so next, the idea was to combine that with some adsorption data. So unfortunately, at the moment, we have no really we don't have really constant adsorption constant that can be obtained with FPMD calculation. So perhaps it will come in the future. But then, so we still rely on some fitting parameters to model this kind of curves. For example, that's a KD of uranium as a function of pH. So that's data that were obtained by Wood Teenacher, which is here, and Jim Davis at Berkeley Lab. And so one important point is that, in fact, with this model, we adjust to model this curve, we adjust only 3 reactions with uranium. And then we are able to predict the behavior of uranium adsorption in a range of conditions, including in the presence of CO2, different concentration, in fact, of carbonate or bicarbonate in solution. And we are also able to model many data from the literature. So meaning that it improves our confidence in the quality of the model that we have set up. Okay, but there is always a but. Remember, we've combined the different kind of surfaces. So what's a combination? In fact, to do this kind of calculation, you need to have an idea about the proportion of different direction on your class. So you're always looking for new information. So that's a work that we did with Sergei Kreisky, former postdoc that was co-advised with Andrei at Subatec. So between Andrei and me in Orléans and Subatec in Nantes. And so Sergei did some IFM measurements in which he was looking at, so it's a Cunipia sample, so he was looking at the orientation of the edges. So he got also some information at atomic scale in order to reorient the particles, in order to have an idea about, yes, the real direction that we got. So, and then he was able to compare that also with molecular dynamic calculation in order to be sure that the direction he has obtained from some observation at the atomic scale on the IFM was in agreement with, okay, what theoretically he should have obtained. And doing all of this work, he was able to have an idea about the proportions of the length of the edges as a function of the orientation. And here you can see that, okay, so the edges that are the main direction are perpendicular to the 010 direction and 110. So we are not too wrong. So in the from previous model, we took a 50-50%. So in fact, it's more about a 30-70% that we should take into account. But there's always a second but, many others. Okay, so perhaps, yeah, most of you, I imagine, know about the structure of clay layers. And so you can have tetrahedral octahedral sheet, but you can have dioxhedral smectites. So here we're interested in so moronite, so it's dioxhedral. But in the dioxhedral system, we can have 2 different structures, a transvacant or cisvacant structure. This is a transvacant, this is a cisvacant, so not exactly the same, but this is symmetric, axis symmetric, this is not axis symmetric. So meaning that each edge is not the same as this one with regards to crystallography. So meaning that all of the sites here are not the same as here, so should not have the same properties. Okay, how do we have a transvacant or cisvacant? If you look at the literature, most monazite are supposed to be cisvacant or have been measured to be cisvacant. We are able to confirm that with this same high resolution scanning transmission electron microscopy. Here it's the prediction of what you should get at the atomic level with a transvacant structure on the signal. This is what you should get with a cisvacant structure looking from the top. And so you can see that definitely we have a cisvacant structure. Unfortunately, all of the calculation that's shown before, FPMD calculation, that have been done on a transvacant structure. So we are back to FPMD calculations. And so I was very fortunate to have this, collaboration just starting with very gifted PhD students at Penguin Gao, who did plenty of this calculation in a very short amount of time. And so he was able to reproduce this kind of calculation made on transvacant system to a cisvacant system. So you can see that you have many, many more type of sites and type of acid-base properties. And then combine this also with the information about the direction of the edges. And here are the results. Okay, so you can see first that there is a good agreement with the titration. So titration data are taken from this paper from Duke from 2005. So we consider that the best data available for titration. And you can see first that, okay, we can get a very good agreement with the data, but you can see also that there's not so much difference with a transvacant model. So meaning that here we have very few constraints about what we should implement in a model if we just stick to the acid-based titration data. So it's not yet a confirmation that the model is okay. So, but still it's interesting. What's most interesting in this new model, it's not the fact that it reacts the same way as a transvacant model. The thing is that the surface charge and surface potential as a function of the crystallographic direction is quite different. And for pH less than 6, in a transvacant model, all of the edges are negatively charged, but for cisvacant clay model, then you have the particles that seems to be polarized. So that's maybe that has important applications. We are still exploring that. So for example, this could have application for anion adsorption on clays. So not a lot of anions are sorbing on clay, but some do, like arsenic. And so you can see that the arsenic 5, for example, adsorption start to decrease at pH 6 approximately. So there are lots of other applications. Perhaps I would be happy to discuss that with you only at the beginning. Okay, that's for cations. Let's go to anions. Anions, some anions do so, like arsenic, for example. But for some anions, instead of having a nickel reconstitution that is less than the initial one, at the end of your experiment, you will get a nickel reconstitution that is more, meaning that we have what was called many years ago negative adsorption. We repel the anions from the surface. Okay, negative adsorption was used to calculate surface area from measurement from solution. So how we can do that? Okay, so this negative adsorption due to the fact that you have this negatively charged layer, and then the cations are attracted to the surface and the anions are repelled from the surface. That's what you can see here. There's less chloride here than sodium, but overall there is the same number of negative charge as the number of positive charge on my sketch, okay? So you have a solution that is not electroneutral in some domain in the water. We can calculate a profile of constitution using, I would say, simple equation. That's a Poisson equation combined with the Poisson-Boltzmann equations, gives you what we call the Guy-Chapman model and the Poisson-Boltzmann model. And then you can get, for example, in that kind of example, with a core that is 40 angstrom wide, this chloride constellation that is far less than the sodium constellation. Okay. Now we can simplify the system. If the layers are separated infinitely, then no interaction between the diffuse layer, very dilute fluorinated suspension. So you have this profile given a Poisson-Boltzmann equation, but you can also simplify the system by saying, okay, so this is equivalent to average anion exclusion distance. You simply equalize the integral below, above the curve. So it means that the area here is the same as the area here in this box. If you do that, so you can obtain an analytical solution, and that is dependent on the Debye length, which is itself dependent on the ionic strength and on the electrostatic potential at the surface. And this one is related to the specific surface charge that you have in the system. Okay, so if you take this exclusion distance that you can calculate here as a function of ionic strength here, so with Debye length here, you multiply this by your surface area and you get an exclusion volume. So if you have measured an exclusion volume, then you can get the surface area. So that's how it works. So this is exclusion volume that has been measured many years ago. There are treasures hidden in very old papers about this kind of experiments. So you can see here, for example, in the smectite sodium system. Okay, so you have these experimental points. So if we take the surface charge of the clay, then you obtain a surface area that is about 600 square meters per gram, a little bit less than 750 square meters per gram. That is a vertical surface, a specific surface area of this clay. Other offer, so approximately the same value. Okay, so we can ask what's the difference from what is coming on. Okay, so if I dezoom this, so you can see the change as a function of the surface charge that is related to the exclusion volume. You can see that, okay, so if I go to larger separation, so to lower ionic strength here, you can see that you have a linear part here, and the linear part are always parallel, whatever the charge on the surface. What you observe here is that if you change the cations, the slope is changing. Okay, so the nonlinear part is in this region, I would say, on this graph, and then you are on the linear part. So meaning that this cannot be due to a decrease of the surface charge. So the only explanation that you can give that is straightforward is to say, okay, we have a decrease in the specific surface area. So with lithium, we have less surface areas, we have more that is available than with cesium, for example. But the specific surface area is something that is specific to the material, right? So it should not be specific to the ions that are interacting with it. Okay, so one simple explanation is to consider that here, so you sketch two layers that are separated, interacting with diffuse layer interacting or not. So here, so you have a separation like that. So look at the blue color. So the blue color is kind of representative of the chloride concentration in the system. So if you stack the system, so there is perhaps no chloride in this part, but then you get more space for chloride to have access to the water. So meaning if you start to stack your particles, you decrease the anion exclusion. So this it was the way it was it was the way this was explained. So meaning that's more stacking with cesium than for ammonium than for potassium, etc., etc. Okay, so can we verify that the stacking? So we did recently some Sachs wax measurement at Alba Saint-Crochon. So it was done with, especially with my colleague Sylvain Grandjean. So what we did is we took a sample and from here, so it was a clay sample, the dilute 10 grams per liter, so it was a sodium clay. And then we start to increase the concentration in the reactor. And when we made him flow through the sample holder here, and we recorded the diffractometer as a function of time. And here you can see the change of intensity. In fact, it's 0.003 layer to layer distance as a function of ionic strength. So what you can see is that you start having a stacking at 0.24 mole per liter. That's really similar to what was obtained by Norrish was 70 years ago. Okay, so that's just a confirmation of what has been done before, but meaning that the stacking should not have an effect here in this region. It should have an effect only in that region. And so, but the problem with the slope of the linear relationship is not that region. So strange. So perhaps we have something different with lithium. So with lithium, the same, in fact. So we start to stack at even higher concentration. So meaning that, so the difference between lithium and sodium can actually be explained by stacking. And we are more surprised with potassium. potassium, we start to stack. We release a system at 0.10 molar. So meaning again that in this part of the graph, so there is no way this could be two stacking, except if there are some experimental procedure that we do not control because that's data taken from the literature. Okay, so but we think that these differences cannot be explained by difference in layer stacking. So what could be the problem? So perhaps we have to come back to the accuracy of the Poisson-Boltzmann equation you use, but there's a problem with mole. So the Poisson-Boltzmann, it's an implicit solvent equation, so meaning there is no ion-ion correlation in this kind of mole. So there are many other hypotheses. So perhaps first thing we can do is to compare the Poisson-Boltzmann equations, the results of Poisson-Boltzmann equation with a more complete model, like a molecular dynamic model, in which we can get the profile of cations and anions as a function of the distance from the surface. So that's been done several times, including this work made in collaboration with Ruth and Michael and Ian. And you can see here that in fact, the Poisson-Boltzmann in red is in very good agreement with the what we got from the molecular dynamics. So less for cations, but here we are mostly interested in anions. So for anions, it looks to be quite accurate. So perhaps the reason is not here. So we can always compare model with other models. So the molecular dynamics calculation are themselves dependent on the force field you consider. So let's go from ClayFF. So the other, the previous one was made by ClayFF. And so let's try to see what's going on with another type of force field like PIM, with includes polarization effect. Okay, that's what we got with PIM in the framework of the thesis of Sébastien Crum, now as assistant professor at the University of Nantes. So you can see here that the profile is quite different. So this green and red is ClayFF and the blue is PIM. So the only problem here is that we have only one curve. So it really needs confirmation with more statistics, other constellation conditions. So I can see as a bias for me because, okay, I would really like the Poisson-Boltzmann to be accurate. So yes, I like that. In fact, this is just a problem of statistics, but perhaps it is not. So yes, we really need to confirm or infirm this kind of results to go further on that point. So this can be a reason. Perhaps we do not consider the right anion exclusion from the surface, but it can also be due to another type of effect we did not take into account. For example, we know that we have these osmotic hydrates in that kind of system. So depending on the number of layers interacting in the osmotic hydrates, perhaps we can have some better agreement. Perhaps this change as a function of ions. And so perhaps we can get a better agreement with the Ferri. Or we can also have additional considerations. And here I can, in fact, say you that, so, okay, so go to this talk like Michael Whitaker. So there is some bending effect also in solution, and perhaps this bending of the layers can explain partly what we observed on a microscopic scale. Okay, so even if we do so, I still have problems. I will be very happy if you have any idea how to solve this problem. For elite, we observe the same kind of trend. So, but elite is not swelling, completely different behavior with regard to the charge. So there is something going on. So why focusing so much effort on non-reactive anions and clay mineral surfaces? That's the question. So, okay, so at the beginning, it was because anions are the most problematic radionuclides coming out of this radioactive waste storage system. Now it's more subtle. So I really think that understanding a quantification of anions dynamics may be the key for the coupled process predictions. So why? I will just show you an example of coupled process at larger scale. So that's, you have sodium and chloride in solution. Sodium is not diffusing at the same speed as chloride. In fact, chloride moves faster. So if you do that in solution, then you have some kind of charge separation. This doesn't happen because we have always electron neutrality in a bulk solution. So the charge balance here is due to the fact that the chloride is dragging the sodium and the sodium is slowing the chloride. And this can be taken, this is due in fact to the fact that you have an unused potential that is created in the system that will in fact slow down one of the ions and accelerate the other. So in a compact system, chloride do not have, chloride or other ions, they do not have a clear access to the very small pores. That's, we did a lot on molecular dynamics. Other teams, other groups did a lot on that too. You can stop by at Microrom's poster. I don't know if it's still alive, the poster, but yes, many new results about this kind of exclusion of anions from clay pores. Most important also that we could have a clear idea that, okay, here, the anions in this kind of system, they cannot access, but the water can have access. So meaning the water can diffuse, anions perhaps cannot diffuse. And we have some kind of experimental proof of that in some systems. So it's not really a smectite, but in which we made precipitate some Celestine at the time. So that blocked the bigger pores. So before precipitation here, that the flux of water tracer is a flux of, it was chloride tracer. And after precipitation, of course, you decrease the diffusion of water, but then you have a zero diffusion of chloride. So meaning at some point, the water can go through and chloride cannot. Okay, if you look at the mean pore width as a function of clay dry density, in fact, you can see that at 1.5 kilogram per cubic decimeter, and then you get a size of the pore, mean size of the pore that is of the order of magnitude of 3 water layer or 2 water layers, meaning that, yes, anions, diffusion, anions movement in the clay is very hindered by the structure and the all of the interactions. So it will give rise to plenty of coupled fluxes. So we have seen the example of diffusion current here together, but see, you have always some kind of reciprocal flux, electrophoresis. If you apply a difference of potential, then you can make some cations move toward the cathode and other anions move towards the anode. So, and it's the same with all the type of flux. So meaning here, so that's the Darcy, Ohm, and Fick law. That's what we call the diagonal terms, or the one that are best known by most of the people. But here you have some kind of off-diagonal. That's anomalous properties, I will say. So chemical osmosis, if there is no anions that can go through across this interlayer here, then if you have a high concentration of sodium chloride here and a low concentration of chloride cannot go, so the sodium cannot go either. So meaning that you are stuck with this high concentration here. So if you want to equilibrate the potential, the permeability potential, then you have to flow the water from this side to this side. That's chemical osmosis. The reverse is true. So if you want to push some water in a very thin clay pore, then the anions will be repelled from, yes, it will be hindered. And so the cations cannot move together. So meaning that you will flow water, but the cations and anions will stay on one side. And that's called fluctuation. That's the principle of reverse osmosis. And you have the same also with electrical flux and fluid pressure. So that's what we call streaming potential and electroosmosis. So plenty of coupled things that happens, and that mostly due to the fact that the anions do not have access to part of the porosity. And so understanding the anions, I think, is a key to understand the coupled processes. Okay, so perhaps we can go through all of this equation with each of the term. I'm not sure it's a good idea now. So I will just focus on one, which is this A. So in fact, this is the equation of flux as a function of everything we could put in it to get all of these coupling parameters. So that's work that we did with Carl a few years ago. And then you get this accumulation terms here that is everywhere. Accumulation is due to the fact that you repel the anions from the diffuse layer, or you attract cations. So more than one for cations and less than one for anions. And if we can quantify this properly, then we can solve this equation perhaps in a predictive manner. So to do that at larger scale, so Poisson-Boltzmann, that's first hypothesis, we cannot do that in reactive transform modeling. So we simplify the system. We use a dual continuum or now multi-continuum system in which we make an approximation. The approximation is about the separation of different type of porosities and the fact that you have homogeneous properties. But then the mass balance between these two representation is good, meaning that you have the same amount of chloride here under this blue curve than under this blue curve here. So that's a key point. So with this kind of model, so we can perfectly predict what happens in this experiment. Okay. We can also predict that, okay, so in a diffusion experiments, what you can see that cations are delayed compared to water tracer and anions. The cation steady state is higher, the anion steady state is lower. This is due to difference, in fact, in accumulation factor. If you do this with a molecular reactive transport modeling we've developed with Carls, and you can perfectly, in fact, predict this kind of effect and get the right parameters for diffusion. This is a single run, so meaning we are not running them all once for the tracer of water, another times for bromide, etc., etc. It's just one run. So we're able to also have an idea about what's going on in a fracture system in which you flow some water, and then you have a matrix that is bordering this fracture, and then we can see the tracer breakthrough at the outlet of the fracture. So it will change completely if we consider the presence of a diffuse layer. Or if there is no presence of the diffuse layer, you can see that, okay, here the different types of cations, anions, and neutral tracer do not behave the same way as if we do not consider this kind of effect. So this can have an influence of what we can predict about special zones, for example, in radioactive waste. So around the borehole or on the gallery, so you have always a disturbed zone, the EESA, and usually it is treated with an equivalent permeability and equivalent diffusivity, the same for, I would say, every species. So if we do some calculation in which we consider a microfracture system, and if we look at the neutral cation anion tracer as a function of time, and with the presence of a salt gradient or without salt gradient, that's what you can see here. So at some point, the conclusion that we can get is that, okay, so neutral cation anion tracer, they do not behave the same way first, or perhaps we should take that into account. So of course, the cation tracer lags behind the neutral and anionics. That's because it is adsorbed, in fact, in the diffuse layer. The presence of fractures enhances for diffusion, so it's not a surprise. And here you can see also the sodium chloride diffuse at the same speed. So the diffusion of a tracer is really not the same as the diffusion of a saline plume. Okay, so I told you that we go to geophysical measurements. So we did not talk about geophysical measurements. So the key here is that we cannot probe the system with a geochemical characterization. We cannot probe the system at other places we would like to probe the system. So the geophysical measurements is one way to do that. But still, we need to inverse the signal, and we need to understand what's going on. So here we propose that, in fact, because we are able to do this, we are also able to do that. And so electrophoresis with the potential of a current that you impose on your system is the kind of electrical geophysical measurements you can do at large or small scale. So meaning that here we have a way to compare what we can do with reactive transport modeling, taking into account the scopal processes and what you can get from geophysical signal. And it's, in fact, the last week developments, we are finally able to this kind of calculation in which we can predict. So this is a current, total current in the system after rejection here of of electrons. Here it's yes, the other part, so the cathode, the anode. And so we can also predict the map of the potential in that kind of system. So by the way, here it's a saline. This part is more saline than the other. In the middle, you have kind of clay, but we cannot see it. So on the map, so by relating the difference of potential to the current you have here, so you get information about the resistivity of the system that can be compared directly to geophysics. So that's very exciting direction that we are taking at the moment with regard to this kind of modeling. And with that, okay, so I'm done. So I do not have really take-home message for this presentation, except a big thank you for listening to me, and also a big thank you to the sponsor of this research. So I've been very lucky to have a PhD grant from Andra, and then Andra was very supportive after that over 20 years with many projects we've done together. So I would like to express my gratitude, especially to Scott Alban and Eric Giffo, who ran this program at the time. And at BRGM, so there was a partnership between BRGM and Andra at that time. So, and this partnership has been, made very easy thanks to Eric Gaucher and Francis Claret. And so other funding. So for 10 years now, I'm also part of the BES project from Ben Gilbert. So I'm very happy to be part of that. And this is funded by DOE. And of course, all of this could not have been done with many collaborations. And I hope I forgot no one, but okay. So I would like to thank everyone for this nice work we've done together. And last but not least, I would like to thank my family and of course, especially Delphine, Estelle, Lucie, and Clément were very supportive of my activity working with mud.
So any questions in the room?
Thank you for a really nice presentation. And I have been working with clays for many years. I love clay material because you have endless, opportunities and questions to ask. I hate it because it's too complicated. Here you show us, even though for simple adsorption behavior, it can become really complicated. And then past that, you have this close diffusion, different, and you have geophysical there. So what I'm really wondering is, as our model become more and more complicated, do we have enough data that we can measure, we can handle to back up the concept? For example, using surface combination as an example, you mentioned that, the potential term has to be calibrated, is model dependent. Then you break down to the basal size and also the edge size, and each size has its own potential. Yeah, it's more mechanistic and actually match the reality better. But do we have data for each potential term to back that up? Then what I really know, then later you show us, eventually we have to match our data with the titration data or simple, so absorption measurement, then we back to the original place. So any comments on the data you feel like you really need to, improve our understanding and the model?
So that's a very good remark. Yeah, so the problem is really about the data, how to obtain them. We cannot study everything at the same level of precision. But the thing is really about getting some sense of what's important and what it's not. So meaning that at the end, so perhaps I can show you, okay, so I have this very complicated model, so I can understand what's going on, but now we can simplify the model. And so perhaps we are not losing too much information by simplifying the model, but we can also give some way of giving some constraint on the domain of applicability of these models. For example, so we had this discussion, so it was on Monday on KED, for example, or on diffusion coefficient, on Ficken diffusion coefficient. In some cases, you can apply this without a problem. In some other, you cannot. So for example, for cesium, I will not apply any KED model. So you need at least a 2 or 3 side model to properly model the diffusion of cesium in a Clayey system. Also, sometimes on a macroscopic point of view, we get some parameters from the experiment that are not physically possible. So I mean, in the framework of what in a theoretical framework, we are interpreting them. So for example, cesium diffusion. So we can obtain porosity, so geometrical factor that is more than 1. So meaning that the cesium will move faster in a clay system than just in pure water. So meaning that something it's not because it's a reality, it's just because there is some additional coupling that makes it happens. It's not a question of diffusion coefficient, it's a problem if I show you on the equation, it's a problem of accumulation in the diffuse layer. So by doing this kind of work, then we can give constraint on the applicability of the model and say, oh, watch, so here you apply this kind of model, but it's not going to predict the thing very well. Best example is a saline plume. So saline plume does not diffuse the same way as a tracer, and yeah, so that's you cannot apply the same model for a tracer and for a saline plume. So you will be wrong on the distance of diffusion of your tracer compared to the plume. So that's, yes, the whole point is about to get this constraint and to get some better idea of applicability of the simplified model. Simplified model is, yes, it's necessary. we can not model everything at the molecular scale. It's not possible. Yeah.
Thanks, Christophe. I hear probably 5 talks of yours a year, and every time I learn something new. So that's great. Thank you.
So lots of progress.
I'm interested in the edge charge work that you did comparing transvacant and cisvacant clays, and ultimately coming to the conclusion that it's essentially the same. And I'm curious if there's something more general there, or would we have to go through that same exercise of enumerating all of the different edge sites for, any clay we would be interested in? Or is there something more fundamental about how the edge charge is ultimately behaves similarly across different types of clay minerals?
Okay, so the overall particle charge as a function of pH remain approximately the same. So we think that based on the morning approach we did, but that's really the average for the particles as a whole. So in meaning it's hiding many differences that we have on each of the edges. And I show you that some of the edges are positively charged while others are negatively charged. So meaning that I will not say it's the same. So I just say that we cannot tell that this is different from that one based on very microscopic measurements. So we would have never discovered this, and perhaps, I don't know. So we are very trustful with regards to modeling techniques to calculate this pKa. So I hope it's completely good, but perhaps in some years, someone else will say, okay, so I have a new metal, and with the new metal, I have other pK value. I can reproduce your curves like you do, because we are not so sensitive to reproduce that, and I have a different picture of what is going on here. So this I don't know, but with what we have done here, so yes, I think that's the most interesting part is this figures on the right. So meaning that there must be some implications. So meaning if we start studying the behavior, so geological behavior of clay layers or clay suspension at pH less than 6, perhaps we should take that into account, because it should have an effect on the orientation of particles with regard to each other's. For anion insertion, so there is bit of anion insertion at low pH, even for I think even for chloride. I'm quite sure that we can find some data for which at very low pH we have a little bit of adsorption that compensate for the exclusion, for example. Perhaps we have to look at that, and it will give some insight about the veracity of this type of model or not. So we need to have this back and forth comparison between modeling and experiment, and we need to think things differently after each of these iterations.
Thank you.
Yeah, thank you, Christophe. It's a great talk. As I guess, a geologist or a geochemist, I'm very excited about your potential application for natural soil, or maybe like, are you thinking about what this new behavior, especially in terms of lithium and potassium, gonna do with the natural maybe soil clay? Many of them probably are associated with precipitation. Do you think about the bigger scale?
That's another bias in this kind of study. So we try to study, I would say, a system that is the most clean as possible. So meaning that we are trying to work with clay minerals that are purified. So in order to really have some data on the clay and not on the coating or this kind of organic matter, iron coating. So yeah, that's another question. Is this really applicable to natural system? So I hope so. But yes, with the type of data okay, I obtained. So I must admit, I've never very focused on the most complex system with regards to adsorption, except in some approaches we did for clay rocks, in which we showed, in fact, that what's really important was all of the cations that were already present in the pore water. So what I show you for, it's not so much for uranium, but for lead, for example. Oops, sorry. This kind of adsorption behavior, you will not get the same exactly in a natural pore water because there's many competitors in natural pore water. So, but if you want to understand this competition, this competitive behavior, then at some point we need also to understand what's going on with the ideal system. So yes, that's ideal system behavior, not natural system behavior.
Thank you very much.